Hello, and welcome back. We're going to switch from the hypersensitivities, where we have an over-response of the immune system, to the immunodeficiencies. All right? This is going to be a lack of an immune response. All right? And our causes or etiologies associated with immunodeficiencies can be congenital, meaning at birth. It can also be genetic, which kind of goes along with something being congenital, all right? Or it can be acquired, all right, through something like a viral infection, and HIV is going to be the example we're going to use there, okay? So the way immunodeficiencies are going to be diagnosed is when there are recurrent or unusual infections, all right? Whether it be an ear infection, a yeast infection, all right? But what ends up happening, the individual has infections that don't clear up. When they're treated, all right? So with immunodeficiencies, all right, the defect can be T cell or T cell and B cell related, okay? With our immunodeficiencies, the example that I'm going to give here, I'm going to have two examples in this video, and then the third example I'll have a separate video for, is going to be what's known as SCID, all right? And that's severe combined, oops, that's an M, not an N. Severe combined immunodeficiency disorder, okay? And with that, you can either have a lack of T cells, but you do have B cells produced. Now, those B cells may not be functional because if you remember from reviewing immunology, you need the helper T cells to activate the B cells to get the antibodies made, okay? You can also have a lack of both T cell and B cells, all right? Meaning the cells aren't produced at all, okay? So typically the lack of both T cells and B cells, this is going to be a mutation in either the RAG1 or RAG2 gene, okay? That RAG stands for recombination activating gene, okay? So what ends up happening with that deficiency you've got a disruption in the receptor antigen sites, okay? You can also have a lack of T cells but have the B cells produced. This one tends to be X-linked, okay? So X-linked is going to be a genetic disorder. Because it's X-linked, it's going to be more common in males because males inherit one copy of the X chromosome from mom. From dad, they get the Y chromosome. So if they have a mutation in a gene on the X chromosome, they're going to show the trait, okay? And that mutation can either be in a CD3 gene or more commonly is a gene known as IL-2RG, which is going to be a cytokine receptor. All right. The severe combined immunodeficiency also is referred to as the boy in the bubble disease. There was a child in the 1970s who was born with severe combined immunodeficiency disorder, and they literally kept him inside of a bubble for the vast majority of his life, okay? He did live into his teen years, I believe, but did not lead a full life because of the severity of the immunodeficiency. So the bacteria that are normally part of our flora, the yeast that's part of the environment, with individuals who have SCID, that's enough to be fatal for them, okay? About 50% of SCID is genetic. It's going to be X-linked. And so there are no T cells produced in these individuals. B cells are made, but they're not activated because you don't have the T cells associated with it, okay? Typically, the recurrent unusual infections associated with SCID happen in the first 3 months of life, all right? There is some promise with SCID now and genetic engineering because we know what genes are involved, so the individual can be given a genetically engineered version of the gene to make up for this deficiency, okay? So with SCID, there are some kind of treatment options out there other than just living their life out in a bubble. But the individuals typically need to go back to make sure that they're getting proper stimulation of their immune system, okay? So it's certainly better, but still not ideal, okay? The other example that I'm going to go over is DiGeorge syndrome. DiGeorge syndrome is also a defect associated with T cells, but what ends up happening you have the thymus that doesn't either develop properly or isn't generated, okay? So the thymus gland, if you remember, is where our T cells mature. If the individual doesn't have a thymus gland or has an underdeveloped thymus gland because of decreased cell division, those T cells are not going to develop properly, and you aren't going to get T cells produced, all right? So you're taking out a large arm of the immune response, and again, if you don't have T cells, you may have B cells that are present. The lymphocytes are there, but they're going to stay in their naive state, okay? So you either have a total or partial loss of the thymus gland associated with DiGeorge syndrome, okay? And there are often other congenital defects associated with DiGeorge, because what you've got is a deletion on chromosome 22. So it's 22q11.2, all right? That's our deletion. So there are other genes in that area that result in other deficiencies. And some of those other deficiencies are heart defects, cleft palate, and very often also learning disorders. Okay? So we've got, for our immunodeficiencies, SCID, DiGeorge syndrome. The other immunodeficiency we're going to cover in this course is going to be HIV. All right, and I've run out of board space, so I can't include it much on this one. But with HIV, this is a viral infection that depletes CD4 positive cells, okay? And I'll have more on HIV in a separate video, all right? Thank you for your attention. Please let me know if you have any